Section 4.2, Precipitation Reactions. Figure 4.4 shows two clear solutions being mixed. One solution contains potassium iodide dissolved in water, and the other contains lead nitrate dissolved in water. The reaction between these two solutes produces water-insoluble yellow solid. Reactions that result in the formation of an insoluble product are called precipitation reactions. A precipitate is an insoluble solid formed by a reaction in a solution. In Figure 4.4, a precipitate is lead iodide, a compound that has a very low solubility in water. Lead iodide plus potassium iodide, or lead nitrate plus potassium iodide yields lead iodide plus potassium nitrate. The other product in this reaction is potassium nitrate, remains in solution. Figure 4.4, a precipitation reaction. Potassium iodide aqueous plus lead nitrate aqueous. When added together, will switch anions, and the lead will join with iodine, which is insoluble in water, and fall out as a yellow precipitate, and potassium iodide stays in solution. Precipitation reactions occur when pairs of oppositely charged ions attract each other so strongly that they form an insoluble ionic solid. To predict whether certain combinations of ions form insoluble compounds, we must consider some guidelines concerning the solubilities of common ionic compounds. Solubility guidelines for ionic compounds. The solubility of a substance at a given temperature is the amount of the substance that can be dissolved in a given quantity of solvent at a given temperature. In our discussions, any substance with a solubility less than 0.01 moles per liter will be referred to as insoluble. In those cases, the attraction between the oppositely charged ions in the solid is too great for the water molecules to separate the ions any significant extent. The substance remains largely undissolved. Unfortunately, there are no rules based on simple physical properties such as ionic charge to guide us in predicting whether a particular ionic compound will be soluble. Experimental observations, however, have led to the guidelines for predicting solubility for ionic compounds. For example, experiments show that all common ionic compounds that contain the nitrate ion are soluble in water. Table 4.1 summarizes the solubility guidelines for common ionic compounds. The table is organized according to the anion in the compound, but also reveals many important facts about the cations. Note that all common ionic compounds for the alkali group, metal group, group 1 on the periodic table, and for the ammonium ion are soluble in water. Soluble ionic compounds. Compounds containing nitrate are all soluble. Compounds containing acetate are all soluble. Compounds containing chloride, bromide, and iodide are all soluble except for compounds of silver, mercury 1, and lead. Compounds containing sulfate are all soluble except for compounds of strontium, barium, mercury 1, and lead. All sulfides are insoluble except ammoniums and the alkali metal cations calcium, strontium, and barium. All carbonates are insoluble except for ammoniums and the alkali metals. All phosphates are insoluble except for ammonium and the alkali metals. All compounds containing hydroxide are insoluble except for ammonium, the alkali metals, calcium, strontium, and barium. To predict whether a precipitate forms when we mix two aqueous solutions of two strong electrolytes, we must note the ions present in the reactants and consider the possible cation-anion combinations, and use Table 4.1 to determine if any of these combinations are insoluble. For example, will a precipitate form when solutions of magnesium nitrate and sodium hydroxide are mixed? Both substances are soluble ionic compounds and strong electrolytes. Mixing the solutions first produces a solution containing magnesium, nitrate, sodium, and hydroxide ions. Will either cation interact with either anion to form an insoluble compound? Knowing from Table 4.1 that magnesium nitrate and magnesium hydroxide are both soluble in water, our only possibilities are magnesium with hydroxide and sodium with nitrate. From Table 4.1, we see hydroxides are generally insoluble. Because magnesium is not an exception, magnesium hydroxide is insoluble and thus forms a precipitate. Sodium nitrate, however, is soluble, so sodium and nitrate remain in solution. The balanced equation for the precipitation reaction is magnesium nitrate aqueous plus sodium hydroxide aqueous yields magnesium hydroxide solid and sodium nitrate aqueous. Exchange or metathesis reactions. Notice in equation 4.5 that the reactant cations exchange anions. Magnesium ion ends up with hydroxide and sodium ion ends up with nitrate. The chemical formulas of the products are based upon the charges of the ions. 2 hydroxide ions are needed to give the neutral compound with magnesium 2+, and 1 nitrate ion is needed to give neutral compound with sodium. The equation can be balanced only after chemical formulas of the products have been determined. Reaction in which cations and anions appear to exchange partners conform to the general equation AX plus BY yields AY plus BX. Example, silver nitrate plus potassium chloride yields silver chloride plus potassium nitrate. Such reactions are called either exchange reactions or metathesis reactions, also called double displacement reactions. Precipitation reactions conform to this pattern, as do many neutralization reactions between acids and bases, as we'll see in section 4.3. To complete and balance the equation for a metathesis reaction, we follow these steps. Use the chemical formulas of the reactants to determine which ions are present. Write the chemical formulas of the products by combining the cation from one reactant with the anion of the other, using the ionic charges to determine subscripts in the chemical formulas. Check the water solubilities of the products. For a precipitation reaction to occur, at least one product must be insoluble in water, and then balance the equation. Ionic equations. In writing equations for reactions in aqueous solution, it's often useful to indicate whether the dissolved substances are present predominantly as ions or as molecules. Let's reconsider the precipitation reaction between lead nitrate and potassium iodide. Lead nitrate aqueous plus potassium iodide aqueous yields lead iodide solid plus potassium nitrate aqueous. An equation written in this fashion showing the complete chemical formulas of reactants and products is called a molecular equation because it shows the chemical formulas without indicating ionic character. Because lead nitrate, potassium iodide, and potassium nitrate are all water-soluble ionic compounds and therefore strong electrolytes, we can write the equation in a form that indicates which species exist as ions in the solution. So 4.7, everything is listed as ions except for lead iodide, which is a solid. An example written in this form with all strong electrolytes shown as ions is called the complete ionic equation. Notice that potassium and nitrate appear on both sides of equation 4.7. Ions that appear in identical form on both sides of a complete ionic equation are called spectator ions. They play no direct role in the reaction. When spectator ions are omitted from the equation, they cancel out like algebraic quantities, we are left with the net ionic equation. which is one that indicates only the ions and molecules directly involved in the reaction. In this case, the reaction is lead ion plus two iodide ions formed to make the solid lead iodide. Because charge is conserved in reactions, the sum of the ionic charges must be the same on both sides of the balanced net equation. In this case, the positive 2 charge of the cation and the 2 negative 1 charges of the anions adds to 0, and the charge of the electrically neutrally product. If every ion in a complete ionic equation is a spectator, no reaction occurs. Net ionic equation illustrates the similarities between various reactions involving electrolytes. For example, 4.8 expresses the essential feature of the precipitation reaction between any strong electrolyte containing lead and any strong electrolyte containing iodide. The ions combine to form a precipitate of lead iodide. Thus, a net ionic equation demonstrates that more than one set of reactants can lead to the same net reaction. For example, aqueous solutions of potassium iodide and magnesium iodide share many chemical similarities because both contain iodide ions. Either solution, when mixed with lead nitrate, produces lead iodide. The complete ionic equation, on the other hand, identifies the actual reactants that participate in the reaction. The following steps summarize the procedure for writing net ionic equation. Write a balanced molecular equation for the reaction. Rewrite the equation to show the ions in the form in the solution for each soluble strong electrolyte dissociates into ions. Only strong electrolytes dissolved in aqueous solution are written in ionic form. Identify and cancel the spectator ions.